friends, welcome to Brace Solution Times. For today's video, we are going to see Theorem 1.7 and Theorem 1.8. So let's get started. Theorem 1.7, reversal law for inverse. So it's otherwise called as reversal law for inverse. If A and B are non-singular matrices of the same order, then the product AB is also non-singular and AB inverse is equal to B inverse A inverse. So first they have given that A and B are non-singular matrices, which means let's write it out first. A and B are non-singular, right? Which means I've already said in my previous videos that if some matrix are non-singular, you have to write two conditions which are determinant of the particular matrix. First matrix is A, right? So determinant of A is not equal to 0, and the second matrix here is determinant of B, which is also not equal to 0, because these both are non-singular matrices. And then this is the first condition we have to put. Determinant of A is not equal to 0 and the B is not equal to 0. And then the second condition is therefore A inverse exists. So these are the constant properties for non-singular matrix, and here B inverse exists. Okay, so these are the condition which we have taken from the first given part. And then if it's a then after the word then you have some things which you have to prove in the future. So then the product AB is also non-singular, which means you have to prove that AB is also non-singular and AB inverse is equal to B inverse into A inverse. So we have to prove two things here, which is AB is non-singular and you have to prove this equality. Okay, now here first we have to prove AB, the product AB is non-singular, right? So what's the condition of non-singular? Which is determinant of here the matrix is A, so I have taken as A, but here the matrix is AB, so you have to take that as determinant of AB is not equal to 0. So this part is what you have to prove, right? Now let's prove it. For proving this determinant of AB, we need a product rule for determinants, because as I already said in my previous videos that you cannot just அதாவது நீங்கள் வந்து டிட்டர்மினன்ஸை வந்துட்டு ஜஸ்ட் லைக் ஓகே நமக்கு டிட்டர்மினன்ட் வேணும் ஸோ அதனால நம்ம அதை போடலாம் அப்படின்னு சொல்லி நம்மளால் எடுக்க முடியாது, ரைட்? மேக்ஸ் doesn't works like that. We need some certain rules and a property to do that. So for that we are taking a rule called product rule for determinants. So and by product rule of determinant, we have determinant of AB. So the product rule for determinant, and we have to prove that AB is non-singular. So thus we can take that as a determinant of AB, which is equal to. So by product rule of determinant, we have a rule that we can separate this determinant, which is determinant of A into determinant of B, right? So we can do this using product rule of determinants. So we already know that determinant of A is not equal to 0, and then determinant of B is also not equal to 0. Therefore, you can say that this determinant of AB is also not equal to 0, right? So therefore, you have found that determinant of AB is not equal to 0, which means AB is a non-singular. Therefore, you can say that AB is non-singular. And then the second thing you have to prove is AB inverse, AB the whole inverse is equal to B inverse into A inverse. So this is what you have to prove, right? For finding this, we are taking two matrices, which is a matrix AB, which we have just found, and then another matrix which is B inverse into A inverse, because we already know that B inverse exists and A inverse also exists, and in order to prove that prove this thing, we need this, right? So we are taking AB into B inverse into A inverse. Okay, and then we are going to use the associative property for changing the brackets, so that you will get A into B inverse. So here we are changing the brackets to these two things, so we will get B into B inverse and the A inverse will be left alone. that side, so that you will get an answer A into B inverse. You can consider that as IN, an identity matrix, right? It can be 1, so instead of 1 I'm writing as it as IN, and then here there is another A inverse, and then here IN will be again an identity matrix, so that you can consider that as 1, so that again there will be A into A inverse only, so that A into A inverse you can write it as another identity matrix. So this is how it works. Okay, and now we are gonna multiply the same thing, solve the same thing but in a reversed manner, which is B inverse A inverse and again A into B. Okay, so while solving this, first what we have to do by using the associative property, you have to change the brackets so that you will get B inverse into A inverse and A into B. So the next step is obviously you have to take A inverse into A as I, so that we'll get into IN into B. So we'll get this, and therefore for the IN we'll substitute IN instead of 1, substitute 1 instead of IN, so that we'll get B inverse into B, and then B inverse into B will be again an IN, right? So we got two things, which is AB into B inverse A inverse is equal to IN, and B inverse A inverse into AB is equal to IN. So I'm taking just any one term, which is I'm taking the first term, which is AB, and B inverse A inverse is equal to IN. So why I'm taking that is this is just the reverse order, right? For here AB is here and here AB is here, and the same terms are multiplied, so that I'm just taking any one element from here. With this will be equal to IN, right? So this is what we have got, and to prove the theorem, first we need B inverse and A inverse, right? I am taking this in the left hand side and then taking this to the right hand side, so that you'll get IN divided by AB. And while we take AB to the nominators, then you'll get B inverse A inverse is equal to IN into AB the whole inverse. So therefore you will get this, and then in the place of IN we can substitute 1 here because it's an identity element. Therefore here there will be AB the whole inverse. Since it's a 1 multiplied by an element, will the answer will be the same element. So therefore we got B inverse A inverse is equal to AB the whole inverse. Therefore this is the theorem of reversal of inverse, and hence proved. Okay, now let's go to the theorem 1.8. Theorem 1.8, law of double inverse. If A is non-singular, then A inverse is also non-singular, and A inverse the whole inverse is equal to A. I guess you figured out how this name where from this name came from, right? Here there is two inverse, which means double inverse, so this is called law of double inverse. Okay, now let's start the given part, which is A is non-singular. A is non-singular, right? Okay, A is not singular, so that I have already said you need to remember two conditions if a particular matrix is non-singular, which is the first condition is determinant of A must be not equal to 0. So if this is not equal to 0, then you can say that A is a non-singular, and then therefore A inverse exists, right? So A inverse exists. If they say A inverse exists, with that means A is non-singular and determinant of A is not equal to 0. Okay, these are the two conditions you have to remember while in a theorem or in a question. They have said that A is a non-singular matrix. Okay, now let's see what we have to prove, that then A inverse is also non-singular. So they have already given that A is a non-singular, and we have found that A inverse exists. Then we have to prove that A inverse is also a non-singular matrix. Okay, so this is what we have to prove, and then second part is A inverse the whole inverse is equal to A. So this is also a part we have to prove. So we have to prove two things here. So let's prove with the first sum, which is A inverse is also a non-singular matrix. Okay. For proving the first part, which is A inverse, this is what we have to prove. Okay, which is A inverse is also non-singular, right? So this is what we have to prove, and then for this, for proving this, you have to satisfy a condition which is A inverse, which means determinant of A inverse is not equal to 0. So this is a condition of non-singular matrix, right? So if you satisfy this condition, then you can say that A inverse is a non-singular matrix. Okay. So we have to prove this first. For proving this, I'm taking some equation from theorem 1.4. I have already explained that theorem actually in my other video. I will give that link in my description, so you can go see that. Okay. So the theorem, by theorem 1.5, we have an equation for determinant of A inverse. So we need determinant of A inverse here, right? So by the definition of determinant of A inverse, by the theorem of 1.4, we have this particular equation there, okay, which is determinant of A inverse is equal to 1 divided by determinant of A. And here you can see that determinant of A is not equal to 0, right? So here there is a determinant of A which is not equal to 0 here, since determinant of A is not equal to 0, which means determinant of A has some number, right? Therefore you can say that this determinant of A inverse also is not equal to 0, because the answer of this is also is not equal to 0. So therefore you can say that this A inverse, determinant of A inverse, is also not equal to 0. Okay. So this is also not equal to 0. Therefore you have proved that determinant of A inverse is not equal to 0. Therefore A inverse is also a non-singular matrix. So let's write it. A inverse is also non-singular. Can you understand it? And the second thing you have to prove that is A inverse, the whole inverse, is equal to A. So we have to prove this. So first let's write the formula of A inverse, which will be like A into A inverse is equal to A inverse into A is equal to I. Okay, so this is the formula, and here you can say these both terms are equal, just the terms are reversed here. So I'm picking just one term here from here, which is A into A inverse is equal to In. So I'm just picking one term from this equation. Okay, now here we need to prove a double inverse, which is A inverse, the whole inverse. So that's why we are multiplying these both sides by inverse. Okay, so multiply both sides with inverse. Okay, so while multiplying we get A into A inverse, the whole inverse is equal to In, right? So by the reversal law of inverse, I have already said that in our previous theorem, the reversal law of inverse. What's the reversal law? First you have to write the second term, which is A inverse, the whole inverse, and then you have to write the first term, which is A, the whole inverse. Okay, so this is called the reversal law, which is first we have to take the if there is two terms with whole inverse, if we need to separate that, then the rule is first you have to take the second element and put a whole inverse in it, and then take the first element and then put a inverse in it. Okay, so this is the way of multiplying it. So here there will be also an inverse, right? But the identity element is nothing but 1. So 1 into inverse, it will be again a 1. So let's put this here, and here in our theorem what we have to prove, A inverse, the whole inverse, is equal to, so in the left hand side we have to leave only this. So we are going to leave A inverse, the whole inverse here, and we are taking this A inverse to the right hand side, so that you'll get 1 divided by A inverse. So A inverse in the denominator, and we have to bring it to the numerator, then it will convert like this, right? It will become a normal A itself, so that our answer will be A inverse, the whole inverse, is equal to A. So this is what we have to prove in this theorem, law of double inverse. So A, the double inverse, is equal to A. Okay, so therefore you can write it as hence proved. Thank you guys. Hope you guys enjoyed this video. If you like this video, please hit the like button and make sure to subscribe. See you in the next video. Bye.